Welcome to Problem Solving for AP Physics C, and today we'll be focusing on center of mass. So to begin with, let's review the discrete definition for center of mass very briefly. And I'll specifically write this out for the x-coordinate of center of mass. We can note this as xcm. This is equal to 1 over our total mass times the sum from I equals 1 to n. We have a collection of n objects of mi xi. So what we're doing is we're taking a weighted average of our positions, weighted by the mass of each individual point object. And of course, our total mass in summation notation can be written as the sum from I equals 1 to n mi. So that's our discrete definition. And of course, we can define the same for the y-coordinate of the center of mass. And in a step-by-step process, step number 1, of course, is to determine a reference point, because without it, we cannot define xi or yi. Step 2 is to compute m total. And then finally, we apply the definition of center of mass to compute the two weighted averages. So for today, we'll be focusing specifically on continuous mass distributions. And to do that, we're going to have to rework our definition. So our center of mass is going to be equal to, well, our total mass is still our total mass, though computing it will look a bit different. What we're doing now is we're splitting our continuous mass into an infinite number of infinitesimal points. So visually, as we'll see in the next problem, for example, if we have a rod, we will split it up into an infinite number of infinitesimal masses, dm, each of which has a well-defined position, x. Our summation will therefore become an integral. Our masses become dm, and x, of course, becomes just x, loses that index, so that we have integral x dm. In parallel, our total mass, m total, is equal to the integral of dm, the sum of all of those infinitesimal masses. So this may seem not very transparent to you. It may not be immediately obvious how we evaluate an integral like this. So let's jump right into a practice problem to see how we apply this definition. So let's actually apply this definition to a particular scenario. We'll look at a triangle with base b and height h and total mass m. So let's rewrite our definition. X center of mass is equal to 1 over m total times integral x dm. And so step 1 in our process is to determine appropriate slices for dm. So what do we mean by that? Well, we want, in order to be able to carry out our integration successfully, we want to slice up our triangle into regions with fixed x coordinate. So in this case, we're going to be slicing it vertically. And as we can see, this is an infinitesimally thin slice, though obviously I can't draw it as infinitesimally thin. It has mass dm and x coordinate, x, a fixed x coordinate. So that's step 1 complete. Now notice that this hasn't really helped us solve the integral. Step 2 is going to be one of the most crucial steps in this unit, which is to rewrite dm in terms of our density. Now, as we'll see, there are 3 types of density: lambda, sigma, and rho, in increasing dimension. Lambda being 1-dimensional, sigma being 2-dimensional, rho being 3-dimensional. For our problem, we're 2-dimensional. Sigma is equal to the m by dA. This is simply the definition of sigma. Now, for each problem, in addition to the definition of sigma, we have the value of sigma. In this particular problem, we have a total mass m and a total area 1/2 bh. And why was this useful? We can now go from a variable of integration that is mass dependent to one that is area dependent, which gets us one step closer to introducing a coordinate system. I can rewrite dm. dm is equal to 2m over bh dA. So let's rewrite our integral. We have 1 over m, and factoring out our constants times 2m over bh integral x dA. And with that, we've completed step 2. So now we come to another crucial step, which is dA is still not a very useful variable of integration. We would like to have it in terms of the spatial coordinate. And to do that, we're going to introduce a coordinate system. And I will set x equals 0, this edge of the rod of the triangle. But of course, you have the freedom to set it wherever you like. It's just, I prefer to make life easy for myself. So now that we've introduced a coordinate system, let's try rewriting our integral in terms of this coordinate system. So step 1 is, let's see if we can write the area dA of this rod in terms of our coordinate system, of this rectangle. Well, it has a well-defined thickness now in terms of the coordinate system as dx, right? This is the thickness of our rod. And it has a well-defined y-coordinate as well. And so what we can say, therefore, is that the infinitesimal area of this rod, or of this rectangle, is y dx. And this is almost good enough, except we want our integral to be completely in terms of x to be able to carry out the integration. But notice that the hypotenuse of this triangle is a straight line. And therefore, we can say that y as a function of x, y is equal to h over b times x. And so with that, we can say that dA is equal to h over b x dx. And so now let's rewrite our integral. What we get is 1 over m, well, our m's cancel out. So we have 2 over bh times integral h over b x squared dx. And then finally, let's put our bounds. And well, we start at x equals 0 and we go all the way up to x equals b. So let's add those bounds and then we're ready to integrate. Notice we have cancellation of h, and so we have 2 over b squared times x cubed over 3 evaluated from 0 up to b. And so this ends up giving us 2/3 b. So let's quickly ask ourselves, does this answer 2/3 b make sense? Well, x equals 0 is at this edge of the rod right here. X equals b is at this edge. We do expect our center of mass to be closer to the taller part of the triangle because there's more mass present there. And so intuitively, our solution does make sense. So let's move on and look at a second problem. And let's consider the case of a non-uniform rod. So we're going to have a rod of length L. Let's indicate that. So we have a rod of length L. And this time we're going to denote our density of the rod. This is a one-dimensional problem because we're going to neglect the thickness of the rod. And we're told that the density of the rod is equal to lambda naught times x. Notice that this is directly introducing a coordinate system. We'll denote this end of the rod as being x equals 0. So what does this mean? This means as we go farther along in the rod, our density becomes larger. Now, as before, we had sigma equals the m by dA. In the case of lambda, which is one-dimensional, the definition of lambda is amount of mass per arc length, or dm by dl. So definition and value. And so if we want to determine the center of mass, let's start by writing out the definition of center of mass, namely xcm is equal to 1 over m total integral x dm. And step 1 is to determine appropriate slices for dm. And in this case, hopefully it is obvious that we will again slice vertically. And so that's step 1 complete. And rewriting dm in terms of a density, in a sense, this is easier this time because we've directly been given the density. And so we can write that dm is equal to lambda naught x naught dl. Finally, in terms of our coordinate system, notice that dl represents motion along an arc, section of arc length. This is very generalized coordinate, but in terms of our x-coordinate, notice that our rod is aligned completely along the x-axis, so that dl, moving along our rod a little bit, is equal to moving along the x-axis a little bit. dl equals dx. And so with that, our integral becomes 1 over m integral lambda naught x squared dx. Finally, what are our bounds of integration? Well, we start at x equals 0 and we move up all the way to x equals L. And so at this point, we can integrate. We get lambda naught over m x cubed over 3 evaluated from 0 to L, giving us lambda naught L cubed over 3n. So that is, I forgot to check off as we went along, but that completes us through step 5. But this time, notice that we haven't been directly given total mass. So we're actually going to have to apply the second half of our definition for continuous mass distributions, namely that m total is equal to integral dm. Well, integral dm, as we've just seen, is lambda naught x dx. And of course, we're integrating along the whole rod, so we start at 0 and end at L. So pulling out lambda naught, integral x dx is, of course, x squared over 2. And we're evaluating from 0 to L, giving us lambda naught L squared over 2. So finally, we plug this into our result from the previous part of the problem. And what we get is lambda naught L cubed over 3 times 2 over lambda naught L squared, or 2/3 L. Now, if this looks very similar to the result from the previous problem, notice that in this problem, we have a linearly increasing density. In the previous problem, we had a uniform density, but the height of our slices increased linearly. And so it is not a coincidence that we've gotten the same result for this problem. So let's move on and consider the case of a curved rod with radius r, uniform density, and total mass m. Notice that in this case, we're not going to need to compute the x-coordinate of the center of mass, and that's because visually, hopefully you agree that due to symmetry, the x-coordinate of center of mass is at the center of the rod. Instead, we're going to be finding the y-coordinate of the center of mass. Step 1 will indicate a respective dm. And let's write our definition. Y center of mass is equal to 1 over total mass integral y dm. And so now let's rewrite dm in terms of a density. Well, we're dealing with one-dimensional object, and so we can say that lambda is equal definitionally to dm by dl, and that this is equal to our total mass over our length, which is pi r, half the circumference of a circle. And with that, we can rewrite our integral. We have 1 over m integral y, and dm is replaced with m over pi r dl. Excellent. And so we can, of course, simplify this down to being 1 over pi r integral y dl. And now it's time to introduce a coordinate system, but let's indicate what dl looks like along our rod. dl is no longer neatly aligned with a y or an x-axis. Instead, if we recall our polar coordinates, dl moves in the d theta direction. And in fact, if you recall your coordinate systems, dl is equal to r d theta. And so with that, we get 1 over pi r integral y r d theta. And of course, now our job is to rewrite y in terms of theta. If we sketch our angle theta over here, we notice that our y coordinate is equal to r sine theta. And so rewriting our integral, we have 1 over pi r integral r sine theta r d theta. And what are our bounds? Well, we start at r equals 0 when we're here. At theta equals 0 when we're here, and going all the way up to theta equals pi. So our bounds are 0 to pi. So taking out all of our constants, we have r over pi out front. And the integral of sine is minus cosine. So we have minus cosine theta evaluated from 0 up to pi. And so this becomes 2 times r over pi. And so once again, let's check our intuition. We have more of the mass concentrated towards the top of the circle. And so it makes sense that our y coordinate of the center of mass would be more than halfway up.